SwayamPrabha. Digital India. Educated India.
In this lecture, let us have a look at the governing equations of Inviscid high temperature non-equilibrium flow. Before we go over to the non-equilibrium governing equations, we will have a quick recapitulation of the conservation equations for equilibrium flow. We have looked at those forms in earlier weeks, especially the second week of the course. It is a good time to have a recapitulation of those different conservation equation forms. You may recall about this framework that we discussed in week 2, where we took the conservation equations from different perspectives. First of all, the two broad classes, one the infinitesimal fluid element, the other the finite control volume kind of an approach. And then in those two main categories or classes, we further had two categorizations in the form of Eulerian and Lagrangian forms. And you can see here that when we look at the infinitesimal fluid element, we all have the differential forms, the differential form of the partial differential equations. Moreover, when we are following the fluid element, that gives us the Lagrangian form. We also have the use of the substantial derivative or the material derivative. And you can look at the continuity equation, the momentum equation and energy equation. You can see the body forces figuring in the momentum equation, their influence also coming in the energy equation. Additionally, in the energy equation, you have the provision for heat transfer, and as far as the stresses are concerned, you have the sigma ij term. We will look at the detailing of the sigma ij term in the subsequent slides. Moving over to the finite control volume approach, that of course refers to the integral form of the governing equations. Again, the continuity, momentum and energy equations coming up over there, and the substantial derivative figuring in the Lagrangian form, where we follow the fluid element. The Gauss divergence theorem basically communicates between the fluid element and the control volume approaches. That means essentially the differential and the integral approaches. This was of course the general form. Looking at the stress equation, which of course forms a very important part of those transport equations, especially the momentum and the energy, we see the splitting into the normal stress component due to pressure, the shear, the viscous stresses, the bulk modulus or volumetric stress, and here is the segregation that we can see of the three components. Further, when we take a Newtonian fluid, we know that the shear stress can be represented using this equation tau ij, where essentially this goes to 0 and the beta becomes the molecular viscosity mu, the superscript n becomes 1, which basically gives us the linear behavior for the Newtonian fluid. It is different from 1 for non-Newtonian ones, and if you club the two forms that we see in the boxed format here, you finally get an expression for sigma ij, where we see the application of all the conditions that we discussed already. You see the term lambda, which is the bulk viscosity coefficient. Now, if you look at the normal stress components, then they show up in this form. In each one of those equations you can see the presence of pressure as well as velocity derivatives associated with the viscosity coefficient and the bulk modulus related term where the divergence of the velocity vector is figuring. When it comes to definition of mechanical pressure, it is essentially the compressive stress, and in terms of the sign it will be negative. It is 1/3 or the average of the sum of the normal stresses sigma xx, yy and zz. This average compressive stress is what is going to give you the mechanical pressure. Finally, you see that you can segregate out the thermodynamic pressure here in the expression, and you are left with another term related to the bulk viscosity coefficient, the molecular viscosity put together in this expression times the divergence of the velocity vector. And according to the famous hypothesis of Stokes, we know that the bracketed term goes to 0, where essentially there is no difference between mechanical pressure and thermodynamic pressure, but that is not necessarily consistent at all conditions. So, we generally continue with this expression by retaining the lambda plus 2/3 mu expression, and we call this as the bulk viscosity, and this term essentially gives the difference between the thermodynamic pressure and the mechanical pressure. Moving on to the inviscid form of the equations, of course, the shear stress goes to 0. In this week we are of course dealing with the inviscid equations, so did we in the week 8. Therefore, the sigma term would reduce to this, and here we have not shown the body forces, but if you did, you would actually have compressible hydrodynamic Euler equations, which we discussed in week 2. The E term in the energy equation is defined in terms of internal energy and the kinetic energy, and then more detailing on the values of the bulk viscosity for different media, for example, molecular nitrogen, methane, argon, etc. And it is an important point to recall that the mu resists the inertia of fluid particles during motion, while mu bulk resists compression during high applied pressure on the fluid element, and high applied pressure is an inherent feature of high speed aerodynamics, especially the hypersonic and hypervelocity flows that is considered as a part of this course. Therefore, the effect of mu bulk is not trivial. Having said that, if you write those equations in the vectorial form instead of the index notation that we were using, then we see the continuity equation, the momentum equation, energy equation with definition of stagnation enthalpy, and the equations of state represented at high temperature in the form of correlations, which could be of this form, where temperature and pressure have been shown to be functions of density and enthalpy, for example. And you may recall that in the previous week's lecture we did look at these equations briefly. It is a good time to look at them at a little more detailed level once again in this week, now from the non-equilibrium perspective. We need to understand where the difference or differences come up. One of the major differences that come up is inclusion of the species continuity equation. The one that we have over here is what is going to be referred as global continuity equation, which is in the sense of the gas mixture, while we need to track the evolution of different species in the gas mixture in a non-equilibrium environment, for which we would need to devise species continuity equation for each of the species which participate and form the gas mixture, and we need to figure out the concentration of these species in a time dependent manner. For that, we quickly recall the continuity equation from basics. So, when you look at a control volume of the form like this, you recall having accounted for the two main effects of mass flow rate through the control volume. One was the time rate of change of mass inside the control volume given by this volume integral, while the surface integral took care of the net mass efflux through the control surface. So, we had the definition of the volume as well as the surface when we drew this control volume, and we of course indicated elemental surface area and elemental control volume within the total volume, as well as the presence of the velocity field in the form of the velocity vector here, as well as the streamlines of the flow. When we use the index notation, the velocity components of the velocity vector v is written in an index form, and all possible values of the index have to be accounted for. This is something that we have discussed in week 2. You may recall about the variation of the j index to form the different components of the velocity, and that is what figures over here, dotted with the respective components of the surface vector as well. So, you see the surface vector represented over here in this form, where you have the scalar representation of the elemental surface area times the unit normal n vector that we show over here. We also note that the index notation connects with the vector notation in a form like this, which we show through the boxed expression, and a dot product essentially yields terms of this form. Having recalled that, let us move on with that idea to frame the species continuity equation. So, here what are we talking about? We are talking about chemical non-equilibrium, and therefore, the chemical rate equations have to be incorporated into the species continuity equations, which we will have to do subsequently. First, let us look at the derivation or the form of the species continuity equation before we plug in the rate equations into it. First of all, we look at the mass of the different species per unit volume of the mixture, and accordingly we define the partial densities, if you like, along with the mixture density, and we have a connection between the two in this form. The mass of species I inside the control volume is as usual given by this form, like we saw in the case where there was no mass retention or formation from the control volume. The mass flow out of the control volume was given by this. Now, the difference comes up over here. We define a term W I dot, which is the local rate of change of rho I as a result of chemical reactions which may be taking place inside a control volume. Typically, it may look like this, where you are looking at a box inside which essentially some chemical reactions are going on in high temperature air, and you are trying to monitor them under a non-equilibrium environment. Hence, the net time rate of change of the mass of the species I inside this box is caused due to net flux of species I through the control volume surface and the creation or extinction of species I inside the control volume, naturally leading to a volume integral of this form. This integral equation can be changed to its differential form using the divergence theorem, where the W I dot term would be mass per unit volume per unit time. Therefore, it is a rate term. This is more like a source term in the species continuity equation, and you now must have noted that we have written the continuity equation in terms of one of the species, which can be indicated by the rho I term, and this term comes from the rate equation for the species. For example, the rate equation for NO, if you wish to recall, this is something that we had discussed in detail earlier. So, in the species concentration equation written in the form of a rate equation. We have moles per unit volume per unit time, and therefore, the W dot when you apply to NO would have to be written in the form of a product of the molecular weight of the species MNO times the time rate of change of the NO concentration. So, MNO is basically the mass of the species per mole of the species. In this case, it is NO, and here the kind of equation that we see for the ddt of the NO concentration is of course based on the chemical reaction model that we have considered for high temperature air under non-equilibrium. We will briefly recall that too. So, this you may be able to very easily recall from an earlier lecture where we had proposed this model for high temperature air in chemical non-equilibrium, and it is valid up to a temperature of about 9000 Kelvin or so. We exclude ionization reactions which will come up above that temperature, and here since we are trying to look at the reaction rate equation for NO, it is going to be relevant for us to look at only those chemical reactions which are involving either the dissociation or destruction or production of NO. So, we find that out of the 3 different dissociation reactions that we have over here, the circle one is the one which is relevant for us. That is the destruction of NO into its atomic elements, while there are 3 equations where we see the production of NO, and the possible collision partners are mentioned over here. There could be N2O2 NOO, N plus NO and E minus as possible collision partners, and with these collision partners you can think about devising the different equations which will emerge. We see that the chemical equations 3 to 6 involve production and destruction of NO. Therefore, all of them are relevant when we derive the chemical rate equation for the NO concentration, and we account for the different collision partners for the equation 3. This is the first one that you can think of, where the collision partner happens to be molecular oxygen. You work out the stoichiometric mole numbers and accordingly fit it into the rate equation. So, if this was the only equation we were looking at, we would only have one rate equation, but in our case we will have to look at more of these equations, and therefore, we move on to the others where we account for the possible other collision partners, and that is how we are able to figure out the different equations that we have over here. There was a small slip over here. This should have been NO plus, which you notice in the equation over here, equation F. Finally, all these equations should find their place in devising the ddt of NO. You work out the stoichiometric calculations which are shown over here, and finally, when you devise the ddt of NO, you account for the dissociation reactions accounting for the different collision partners. Additionally, you also look at the bimolecular exchange reactions which lead to production of NO. So, that is basically the form that we had mentioned earlier in the species continuity equation. Now, coming to the differential form of the species continuity equation for NO, it would then be written in a form like this, where instead of calling it I, we have made it specific, we are calling it as NO. So, the left hand side of the equation equates to the W dot, further to this form where the molecular weight times the concentration, the time rate of change of concentration term comes up. If we have n different species in the mixture, we would have n species continuity equations like the ones we have shown above. And of course, for each one of the species we have to include all relevant chemical reaction equations and thereby develop the corresponding rate equations like the way we did for NO. Finally, out of the n of them we utilize n of n minus 1 number of species equations, and then we keep one for satisfying the constrained equation which we call as the mixture density, and thereby we have a n equation system. This is usually the procedure that is followed. Now, if you look at the species concentration, the species continuity equation, this is the way we have represented it. There are alternative ways of representing it too. Here we have included the mass fraction of species, and you see the incorporation here. Again, you can expand the two terms on the left hand side of this species continuity equation. Two of the terms form this, while the rest two form this part of the equation, and you find that the first set of terms essentially gives you the substantial derivative of the time rate of change of a certain quantity, while the second one vanishes due to the global continuity equation. The substantial derivative essentially means that you are going to follow the fluid element and you are going to represent the time rate of change of a quantity as you follow the element. Here you are following the element and you are monitoring the mass fraction. If you are following the element and monitoring the mole mass ratio, then the form of the equation will be like this. Therefore, you see different alternative forms of the species continuity equation being represented here. So, that was how we would incorporate the chemical non-equilibrium into the model, into the conservation equations. So, we see the inclusion of the species continuity equation, which is a very, very important addition in this non-equilibrium perspective from the chemistry angle. Now, we look at the vibrational non-equilibrium part of the problem and see how the vibration rate equation can be included into the conservation equations, where we address the different species in the gas mixture. We know that under equilibrium, the E vibe as well as the E vibe equilibrium term essentially gives you the same expression. However, under non-equilibrium, we end up solving this ordinary differential equation, which is the vibrational rate equation. Now, this vibrational rate equation, if extended to a moving fluid element, would involve the substantial derivative, and essentially there is no other change in the equation apart from the substantial derivative coming into the equation. And then we recall about the two temperature model of part which we were discussing towards the end of the previous lecture, because this is the most effective way of coupling the interaction between the non-equilibrium chemistry and the vibrational aspects. Both vibrational and chemical non-equilibrium, when they simultaneously exist, would have to be suitably coupled and incorporated through the model that we are trying to use here, and Park has suggested a very elegant way of addressing the issue. The basic idea being that the molecules at higher lying vibrational energy levels, which are highly excited vibrationally, are more readily dissociated by molecular collisions. Thereby, molecules will dissociate into atoms. This explains how vibrational relaxation rates and chemical reaction rates can get coupled. and we said that we define an instantaneous vibrational temperature for the species. We call it T vibe, and that governing a local Boltzmann distribution of particles over the vibrational energy levels at the temperature T vibe would be governed by a value satisfying this equation. So, the T vibe must be satisfying this equation, where the instantaneous non-equilibrium value of E vibe is plugged in, and based on that we proceed and we find that higher the value of T vibe, the more the number of particles in the higher lying vibrational energy levels, and this essentially means that it would be easier and faster for the gas to undergo dissociation. To account for this augmentation effect on the chemical rate constant, Park suggested the instantaneous vibrational and translational temperatures be combined, and he proposed an average temperature T A, which is nothing but a geometric mean of the instantaneous vibrational and translational temperatures T vibe and T respectively. So, if you take the geometric mean and get the average temperature, this is the most effective way of coupling the effects, and then the T A based on the above equation needs to be used rather than the T to calculate the chemical rate constants, and there comes the augmentation if you are already talking about larger T vibe values than the equilibrium ones. And when the gas is in vibrational equilibrium, you have a situation like this, and hence the average temperature gives you back the translational temperature, and when it is not, then T A of course produces a different value. So, this was the Park's model, which is a very important one in this context. Now, let us go back to the remaining conservation equations that we need to discuss. The global continuity equation, where we see the density of the mixture, which is of course coming from the sigma rho I term, and it is essentially linked with the species continuity equation, which we have looked at in at a detailed level already in this lecture. We saw different forms of it. So, you saw the forms where you can have a substantial derivative coming in and applying on a particular mass fraction or mole mass ratio form of the equation, and you will be satisfying these constraints when you solve for the mixture. And further, you look at the momentum conservation equation in the global sense and the energy equation, the energy conservation equation in the global sense too. If you recall that when we were discussing about the governing equations for equilibrium flow, we did not mention this, it could have come there too. Here we have mentioned it, and we say that it will be 0 for flow across say a shock wave, which is adiabatic in nature involving no heat transfer, but it would turn out to be non-zero and positive for a gas on which there is an incident laser beam, or you are burning fuel in the gas like it happens in a rocket engine and so on. Therefore, for a general situation you may like to include that Q dot term. You have the equation of state in which you have the specific gas constant, which is defined in terms of the universal gas constant and the molecular weight of the mixture. The molecular weight of the mixture again is calculated using the contribution of the different species, and finally the enthalpy of the mixture, which is also essentially a collective form coming from the effect of the different species in the mixture. Let us conclude now saying that in this lecture we begin with a recapitulation of the conservation equations for equilibrium flow. all the different forms were put together and reviewed, which we had done in much detail in week 2, and with particular stress on the Inviscid equations, that is the Euler equations. Subsequently, the governing equations of high temperature Inviscid non-equilibrium flow were discussed, especially the species continuity equation was derived, which is a very important addition. The incorporation of the chemical rate equations and the vibrational rate equations in the governing PDEs was explained. Thank you.